Welcome back to my lecture, Mechanical Properties of Materials, course number 315008. I'm Klaus-Dieter and we are writing the spring semester 2022. Today I like to open a new chapter, namely to talk about dislocation theory. We have talked about plasticity in the last week and the beginning of this week. We have introduced plastic deformation, strain stress curves, and yielding criteria. Now we want to investigate some mechanisms, particularly one mechanism of plastic deformation in crystalline materials, which is called dislocation theory. First of all, I like to introduce a few general aspects about deformation in a crystal and calculate the theoretical yield strengths according to a simple slip model. So what is plastic deformation? Plastic deformation is where we change the arrangement of atoms in the crystal. So let's assume crystalline materials here, or polycrystalline materials. Here to the right we have a photo from Cuban 1971. The deformation of a single crystal by shear. So we have originally a single crystal here, and then they apply shear across this plane, and what we can observe is that the crystal slips on that plane. So there's basically this crystal plane, maybe it jumps from one plane to the other, but basically it slips off a crystallographic plane. And that is also schematical in this sketch here under a tensile experiment. So we apply a force here, uniaxial force, as you have seen it before, and eventually go to plastic deformation occurring on planes. So we have planes slipping off in this way as shown there, which also means if the two ends are fixed, we also get a rotation of these crystal volumes. So how do we understand plastic slip in single crystals? We start with a crystal lattice. Just let's take one grain here, one perfect grain. No defects inside. And we see these lattice planes. So now we can apply a force here and cut the crystal virtually along this lattice plane, and then displace this lattice plane by one lattice parameter down, by one translation vector down. And then we remove that force, that stress, and end up with the deformed crystal. So it does not go back, because also here we have perfect crystal planes. So before, at the beginning, we had perfect crystal planes. Then we apply stress, respond by slip, so we get plastic deformation. We get that step here at the surface. We get a step here and a step there at the surface. This is shown schematically here on the slide which I showed before. The idea is this slip process, what is happening there in detail. So first of all, we have to look then to the interatomic forces, because if we cut the crystal plane at that location, then of course we have to take the atoms a little bit further apart than in the potential minimum where they are sitting. So you may remember from other courses, chemistry, quantum chemistry and so on, physics, that there are attractive forces and repulsive forces in an atomic binding. So we have two atoms and we can bind them together, we can bring them together. Eventually, when they superimpose, we get strong repulsive forces. That means the spheres, they are hard to penetrate into each other. They can penetrate a little bit, but there's a strong repulsive force due to the electronic interactions, the electron shell. So we can say they're hard spheres, and when they touch each other, we have to deform the electron shell, not just the atom or the binding atoms, the electrons. And also we know there are some attractive forces due to various binding models. There are the covalent bindings, which are strong, some electrons which are shared between the atoms, and there are van der Waals binding forces. There are electron clouds in the metal and having quantum mechanical wave functions, and they can have a binding character and an anti-binding character, as you may know. So we have the attractive forces, which is usually very long range order, and then we have the relative short range order, higher potential repulsive forces. If you put them both together, we get this energy landscape here with a minimum, and that's where the atoms are sitting. So if we bring the atoms apart, we have to go up this potential hill here, and that costs energy and stress. So if we come back to the strain stress curve, which is advertised here as the richest test existing in mechanical testing, there are others as well. We remember there is the elastic strain, and then there's the plastic strain. So what's happening here in this regime? According to the displacement of lattice planes, if we start with the top figure here of a crystal lattice and look, for example, to the black atoms, we just mark them somehow and displace them. So if we displace the first with respect to the second plane, then we get this configuration here in C. And then we can displace the second to the third, which is also shown here in the C, and so on. We can do that stepwise, from the bottom to the top, or from the top to the bottom, or mixed. Eventually, the black atoms, which are aligned here as nearest neighbors, they get further separated by these vectors here. So each of them is slipped by that vector, and later on we call that a Burgers vector. Macroscopically and atomistically, it is shown again in those figures. We have the crystal lattice, we have the green column, and the green column can deform. So let's say if every second plane slipped, not each plane, or every third plane or 10th plane, then we can define an average deformation angle gamma, as shown here. The steps, they're microscopic, and the surface, they make up a surface macroscopically. Now, in this model, when we move a plane from here, the atoms from the location A and to B, and B to C, and C to D, and so on, means we have the bottom plane, let's say this is static, and then we have the top plane which we want to slip. And that top plane, of course, the A atom has to overcome here this potential maximum over this atom, this little potential here. So we need to lift up the upper plane until it locks into the B position. Then the A is slipped from the B. And we have to do that for all the atoms in that plane simultaneously. That's the idea, yeah? So we have stiff planes. We just cut along the plane. We need to lift it up to come over this round corner of the atom, of the other atoms, the ripples. We need to get over the ripples and then sit into next potential minimum. And what is the energy and what is the shear stress we need? So the energy can be translated to a shear stress. So if we look now as a function of displacement of the top layer with respect to the bottom layer, then we have this oscillating function. So we sit at 0, here A sits in the minimum, then we need to go up here, we go to a maximum, we go eventually, when the balls are on top of each other, we get to an unstable equilibrium, and then the ball rolls down, or the whole ripples go down into the next minimum. So overall we get this sinusoidal function of shear stress with respect to the displacement. We can amplify that here. So we want to shift, displace the top atoms with respect to the bottom row of atoms. The displacement is the ux and the shear stress is the tau yz. Because to pull it up, yeah, we have here the potential of the bottom atom, we have here the potential of the top atom. So to pull it up, we do that by shear stress tau xz. We go by pulling in the horizontal direction, we get a component which goes up the hill, and that displaces the atoms up. That displaces the layer up along the z direction. So we call this a lattice parameter A, or lattice distance A, and this we call the displacement vector B, because after this it is periodic. As I say, B like Berger's vector. I come to that again. And let's go through the formalism. So we have this sinusoidal function. Let's say we write it down as a sine function, as shown here by the dotted line. By the dotted line, this is our assumption. We describe the potential as a sine function, and the shear stress is a sine function with a critical tau c, which is kind of the maximum shear here, times sine 2 pi over b times x. The 2 pi is there because when x equals b, it has to be periodic. It has to be periodic in b. So this sine function, of course, is an approximation. It depends also on the other neighbors and on the shape of the orbits and so on. So a realistic relationship is maybe shown here by this continuous black line. But we do now, just for the approximation, how much shear we need to get started here at the beginning. For this, we onset this equation. And then, of course, we have the displacement. to get the shear stress, we assume Hooke's law, or we know Hooke's law. So tau, the shear stress, is gamma times the shear strain times the shear modulus G. And then, now we make an approximation, another approximation. We look for small deformation that X is much smaller than B. So we want to know when we start the shear. When we start the shear, this is basically the slope of the sine function when you go out of the equilibrium. So if X is much smaller than B, we can write the argument of the sine function just by the argument. And then for gamma equals X over A, we get gamma equals X over A, and tau becomes G times X over A. So also for very small deformation X much smaller than B, we can write down for the shear stress. So this is actually this approximation here. Tau xz is the sine function again, but then we develop the sine function into the first Taylor term, tau c 2 pi over b times x. So we have for small deformation, we have developed the slope here. X over A is the strain, the shear strain, and we have an equation for tau in the xz direction. So once we have the constitutional equation with the shear modulus, and here we have the equation of displacement related to the stress. So again, I write them down, Hooke's law and the kinematical case, the two equations I've just shown, and we set them equal and get G times X over A equals tau c 2 pi over b times x, or we can get an expression for the tau maximum, the maximum shear stress. This is when you get out of the minimum, because here the shear stress, once you reach the top, one atom on top of the other, then the shear stress goes down. So the tau maximum equals G over 2 pi. So this is a very important result, and it's a strong theoretical result because you will see the implications. The derivation of this formula, the yellow underlined formula, was very brief and rough. You can do it more accurately by putting atomic potentials in, by putting computer modeling on, and etc. But that will not change much of this result. Maybe you get a factor of unity, like a factor of 2 or 3 different. So within the order of magnitude, this yellow equation is a good approximation. That's what we want to have, an approximation of the shear stress for slip of a crystal plane, of an entire plane when it slips along the ripples of the other plane. So because we make this approximation, we can set 2 pi equals 10 2 pi is 6.28 da 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 da. So this is approximately 10, the order of magnitude of 10. So we can say, just for getting estimates, the estimated shear stress maximum is about G over 10, 1/10 of G. And now let's look to experimental results, what people have measured in their lab. So they take silver. Silver is a FCC material. If I look to 2 pi over G over 2 pi, then it becomes 12.6 megapascal. In the experiment, I measure a yield stress of 0.37 megapascal. Oops, that does not fit at all. So the experimental is much smaller than the theoretical estimated by this rough formula. So even if we are a factor of 2 wrong, or factor of 3, or even factor of 5 or 10 wrong, experimentally we measure much weaker. We measure about 3 times 10 to the 4th weaker maximum shear stress than the modeled shear stress. So for silver it doesn't work. Then you go for aluminium. Aluminium, you estimate 11.3 gigapascal and you measure 0.78 megapascal. So the one is gigapascal and the other is megapascal. It's also a factor of 1,000 between giga and mega. So together we have a factor of 10 to the 4. Copper, we get a factor of 4 times 10 to the 4. Nickel, 10 to the 4. Iron, 10 to the 3. Molybdenum, 10 to the 2. 10 to the 1 if you like. So we can question that. Niobium. So here we are 10 to the 2 for those refractory metals. But cadmium again, 10 to the 4. Magnesium, 10 to the 4. Other magnesium. Yeah, so in magnesium we have different slip system because it's not cubic. We can slip along the basal plane, or we can slip along the prismatic planes. So if this is a hexagon, yeah. This is a hexagon. This is the basal plane. And these are prismatic planes. Prismatic planes. So depending on which you slip, but you also qualitatively you get orders of 10 to the 4th difference. Titanium 10 to the 3 different, one of my favorite metals. Beryllium 10 to the 4. Beryllium in the prismatic slip 10 to the 3. So for all the experiments you get much lower yield stresses by many orders of magnitudes, average 3 to 4 orders of magnitudes less than predicted by this yellow equation. So this is why this result is academically strong, because it doesn't match. Something is wrong in our model of the slip. So what do we have here? We look to whiskers. So crystal whiskers, they are very thin crystals and very long, like a wire, and maybe they have one dislocation in the center, but they're very strong. These are the whiskers are the strongest configurations of a crystal which you typically find. But even there's a discrepancy. So in copper, the theoretical strength is 19.6. So here is 19.6, here's 19.1. Same order of magnitude. So that depends a little bit the people who make the table and where they get the values from. But the same, 19 point something. And in the whisker, we observe a slip which is still much lower, but approaches at least 1 order of magnitude less. Not 10 to the 4 orders of magnitude, just about a factor of 6 or 10 or 12 or 7 or 3. So in the whisker, we approach more the theoretical strength given by this yellow equation. So g over 2 pi or g over 10. That means this equation, this yellow equation, is a good estimate for a upper limit of yield strength. But in big normal bulk material, it does not work at all. In whiskers, we approach it. So in general, we have 2 to 4 orders of magnitude discrepancy, and the question is, what's going on? How can we solve this contradiction? Any idea? If you don't have an idea, keep listening to the lecture, and also we refer to the textbook where you can look up further. So much on the dislocations are written in the textbook by Richard Herzberg. Again, this is an example as I have introduced it here, the stiff lattice planes like corrugated cardboard, and now you take one cardboard, you take the other cardboard, and you put the one on top of the other. Then you can do the experiment in your office, in your home, in your dorm, the 2 cardboards, and just displace it with a little normal force, displace it by 1 ripple, then you will see the shear force you need to overcome the ripples. Easy like that. That's a very simple model. But it doesn't work. We are wrong 2 to 4 orders of magnitude. So we have to do something else. We come up with a theory which is called dislocation theory. You may have heard about dislocations. Dislocations are defects in crystals. And here I want to introduce them again and talk more about how they interact with the crystal lattice for plastic deformation, to accommodate plastic deformation. So if we look to crystallographic defects at all, we have electronic point defects. They are 10 to minus 14 meters, so 1 electron missing. You know that from the semiconductors, doped semiconductors. You remove 1 electron, you get some band gaps and so. These electronic point defects, if you localize them, they would be 10 to minus 14 meters, so a classical electron radius. Then we have atomic point defects. You know that from the diffusion class. What are atomic point defects? Come on, you know that? Atomic point defects?
Vacancy.
A vacancy, exactly. That's an atomic point defect. What else?
Interstitial.
Interstitial, yes. And one other.
Substitution.
Substitutional atoms, exactly. So these are atomic defects where you just remove 1 atom or replace 1 atom or put 1 additional atom in. They are about 1 angstrom in size, so 10 to minus 10 meters. This is now resumed by interfacial defects. So we may have line defects, and the line defects along a line, there are the dislocations we will talk about. But there are also kind of stacking fault defects where we have a whole interface There are grain boundaries where we have more distortion at the grain boundary than just a stacking fault. And we may have phase transformations as well, like martensitic phase transformation. This is the interfacial, the displacive phase transformation, where we change the stacking of the lattice planes. And then we have the volume effects. So volume effects can be, you have an inclusion of a different metal or a different phase or an oxide in the steel. Yeah, you have some inclusions, a grain of sand in the cast metal. So those are volume defects. And volume defects, of course, they can be large. Pores, yeah, bubble. So let's look to the line defects, because dislocations, as you will see, they're line defects. And already in 1907, there was not much known about crystals and dislocations. In 1907, Volterra, he calculated already these kind of defects, namely, you have a cylinder. So this is continuum mechanics. This is not in a crystal. This is continuum mechanics. You take a pipe, a piece of rubber. We can do it with steel as well, but the forces are much higher, elastic forces. Yeah. You cut it along this plane, and then you displace it. So here you see there's a step. There's a displacement in the radial direction. And glue it together. And if you glue it together, it has stresses, of course, because of the elasticity of the problem. So here you can radially, or here you can displace it axially. In the axial direction, the radius you keep the same of the top and the bottom part here, but in the axial direction you can displace it. You may even put more material in here, fill that up a little bit, and remove material from the other side. Yeah, so you get those inclined planes, or you can, like a scissor, displace them in various configurations. So this is continuous material. Yeah, there's no periodicity. It's just continuum. You cut it and you glue it together. You've all done that. Yeah, when you make something up, you know, build a model, hardware. Eventually you have to glue it together, and it doesn't really fit, so you squeeze it a bit until it fits. Vito, Volterra. So there's many Volterras. This is Vito, Volterra, Volterra. Il est français, he is French. Here are the books sur l'équilibre des corps élastiques multiplement connexés. So this means about the equilibrium of elastic bodies multiply connected. In this picture, for example, and this is a thick book. The book you can find here. You can download it here, I guess. I downloaded it. And it has a lot of mathematical descriptions, all the stresses and strains. So that here you go into detail if you want to apply the theory of elasticity. You have a thick book, just theory of elasticity, for the many different examples here. Here, for example, they cut along the surface, and they made the cut a little oblique. So they removed some material, cut some material away, and then they put it together under an angle and glue it together, and then look to the deformation of the body. And this is the result. This is the experimental result. You see, it's not round it's not circular, rotational symmetric. It has a bump here, and this you can imagine, because if you remove some material, let's say you start with a round cylinder, exact cylinder, and then you remove a cone of material like this and put it together, then the result will be put these remaining surfaces, this surface and that surface together after removing the material, then you get the picture to the top left. The experiments have been done by an experimentalist, I forgot his name, Grâce à l'ambition, yeah, it's written here. Grâce à l'aimabilité de Monsieur Jonah, ingénieur de la maison Pirelli de Milan. So there's a Mr. Jonah of the house of Pirelli in Milano, in Italy. J'ai pu confronter les résultats du calcul et de l'expérience. I could verify the theoretical calculations and approaches he has done. So Volterra has done all the theory, this mathematics, yeah, theory of elasticity. And this Mr. Jonah, he has created these specimens out of rubber material, cut it out and glued them together and verified the theory of elasticity and the shape, particularly the shape coming out. So it's maybe not so easy exercises, and that was forefront of research in over 100 years ago. So this is published 1907. A thick book is published 1907. Right. So what are dislocations? Now let's come back to the atomic structure. With Volterra, we saw we removed some material. They removed some material here. And with the crystal lattice, we insert some material. So we insert this lattice plane halfway into our crystal. So this is our crystal, and insert the lattice plane halfway. I can show you that. This is a book. I have a book here in my hands. I hope you can see it and if I take a sheet of paper, I insert that sheet of paper into the book, then it looks a little bit like we see here. We insert an extra plane, so extra sheet, into the existing crystal, into the sheets of the existing crystal, and end up with a situation at the bottom of figure 1.3. This is called the edge dislocation. So easily to imagine. The dislocation is a line defect because we say in this dimension the situation is infinite, and we insert a half infinite plane into the crystal, so with this edge, and this edge then ends up there in the crystal, and you see it ends up there in the 3D representation. Let's look along some of the crystal zone axis perpendicular to the insertion and along the edge. Then we see the edge here. So this is shown by this symbol. We insert a plane until there. This is a line defect, yeah, because the line in the other dimension, it is long. This approximation infinite long. Later we can see it curves, it can loop and so on. But it is a line defect. It has been postulated and by Taylor, Orowan and Polanyi in 1936. Now one more thing about the dislocation is the Burgers vector. So the Burgers vector is basically the vector of the displacement of the atoms after inserting one half plane. And we can get that by a loop. Let's say we start here and then we go around, or let's say we start here. Let me start again. So we start here at the position X, and now we go 1, 2, 3, 4 steps up. Then we go 1, 2, 3, 4 steps over. In a normal crystal, if I go 1, 2, 3, 4 steps down and 1, 2, 3, 4 steps over, I should come back to the same location. However, if there is a dislocation inside, then I do not end up at the same location. Then I end up at X prime. So I started at X and I end up at X prime. And the difference between X and X prime I call the Burgers vector B. So this is how I can find dislocations. Let's do the same exercise here. I start there. I go up 1, 2, then I go over 1, 2, I go down 1, 2, and I go left 1, 2. I'm back at the original location X. So in this case, we don't have a dislocation within this path. So there's no dislocation here, yeah? It means every time I go around, which would be a closed loop in a perfect crystal, so same steps up, a certain number of steps over, the first number of steps down, the up steps down, and the left right steps back. If I end up at the same location, there is no dislocation inside. If I end up at a different position X prime, then there's a dislocation somewhere within the loop, because sometimes it's not so well localized. It's difficult to see, you know. So I can do, let's say I start here, I go 4 up, 1, 2, 3, 4, then I go 6 over, 1, 2, 3, 4, 5, 6. Now I went 4 up, I need to go 4 down. So 1, 2, 3, 4, I go down. And I went 6 over, so I need to go 6 back. 1, 2, 3, 4, 5, 6. End up here. Means somewhere in that red loop is a dislocation, and this is the Burgers vector B. Okay, I guess that's relatively easy to understand, and you may have seen that somewhere else before. Now the question is, how does the dislocation contribute to the motion of lattice planes in the model of plasticity? This is demonstrated here. I have several demonstrations like this, but as time is running, I may briefly indicate what's happening here, and we start from here next time again. So let's say we have an edge dislocation at this point, and as you can see, I go around here. On the top I go 3, and the bottom I go 2 back, and 3 would be 1 over. But what I want to say, I have the dislocation here, and now I say, okay, I bound this here. I have this bond now, and the dislocation is moved to this location. And then I bond this and bond this and bond this, and eventually that part is standing out of the surface. So then we have a plastic deformation from a surface which is like this to a surface which is like that, and the other surface is flat. So by moving the dislocations through or over this plane, over that slip plane, we get a plastic deformation, a net plastic deformation at the end. Again, this is showing here at the bottom. So dislocation is here, and then I rearrange the bonds by shear, and this dislocation moves from the left to the right and moves further, and eventually we end up with a perfect crystal which has been deformed. So at the beginning it was flat, then we move the dislocation through, and it is deformed by 1 atomic step. And the whole thing we compare to the caterpillar. So you know the caterpillar, you can see them maybe in the forest there, outside GTIT. And these caterpillars, they lift up some of the body, they make this distance shorter, and the other distance is longer. And this shorter part moves along the caterpillar, and eventually the caterpillar is straight again, but it has moved by a certain distance. So it has moved from here to here, the head. And then you start with the tail again. Then you start buckling the tail, and the tail buckles here, so you start from here and end up there. Good. With this in mind, I would leave you for today. We only have 1 hour. We have a lot of things to talk. I would love to talk with you more. Maybe we see you tomorrow in the office hour. Would be nice to discuss with some of you guys. Otherwise, if you have a quick question, let me know now. Otherwise, wish you a good evening. I see many people leaving already. Bye.